All right, here we go. So this screen, you don't have to write anything down on this screen. So anti-differentiation by substitution. Up to this point, we have been working with definite integrals. Definite meaning they have those bounds a to b. And when we evaluate a definite integral, we end up with a number. So our number is the area under the curve, or the area from the x-axis to the curve. So this is what we've been doing, definite integrals. Now we are going to start talking indefinite. So you can write this down if you want. You can paraphrase what I'm saying. So now an indefinite integral, as you can see, does not have bounds. So there's no a to b going on here. When we evaluate an indefinite integral, we end up with a function which ends up being a family of functions that have a common derivative. What we're going to get back into is that plus c piece. So if I had x squared, the antiderivative of x squared is 1/3 x cubed plus c, because that c could be anything. If I had 1/3 x cubed plus 7, and I differentiate that, I end up back with x squared. So when it says a family of functions, meaning we have that plus c, we have some constant going on, and we could have infinite numbers that we could put in for that constant. And so when we anti-differentiate, we end up with a new function. We do not end up with a number like we do with definite integrals. Okay. All right. Easy way to recognize they don't have bounds. You don't have to write that down. I pretty much said it, but easy way to recognize indefinite integrals if there's just the integral symbol without any bounds. So if I asked you to evaluate this indefinite integral, well, my anti-differentiation properties tell me I can do each piece individually. So this would be x squared dx minus sine x dx. The antiderivative of x squared, remember we add 1 to the exponent and then divide by that new exponent, so it'd be 1/3 x cubed plus c. But then what is the antiderivative of sine? So it's a negative cosine, but we are subtracting, so it subtracts a negative cosine of x plus c. But this plus c, remember, is just some number. Okay, I don't even care if it's a positive or negative number. It's just some number that's going on. So I could write this as 1/3 x cubed plus cosine of x, because I'm subtracting a negative, and I'm still going to leave it as just plus c. Okay, that plus c, you can always write it as plus c, because even if c is some negative number, all it's representing is some number. And when I differentiate that number, it goes to 0. Doesn't matter if it's a positive or a negative, it's going to go to 0. So this one, if you are asked to evaluate, this is as far as you can go. 1/3 x cubed plus cosine of x plus c. And you can always check it. If you were to differentiate this, you should end up back here at x squared minus sine x. All right, but then there's a lot that we can do with indefinite integrals. This is what I passed out to you to start. So all of these properties of indefinite integrals. This is kind of just for your reference. You don't have to memorize these. A lot of these are pretty intuitive. There's a couple of them that I want to pay attention to. This one right here we're going to talk about. And this one right here, we are going to talk about to do some examples with. That power formula, this one, is fancy notation for adding 1 to the exponent and then dividing by the new exponent. So they just have it written as u raised to the n plus 1, all divided by n plus 1. We've already been doing that. Add 1 to the exponent and divide by that new exponent. All the trig formulas, you already know these. They're just writing them as antiderivatives, but we know those trig formulas well enough that we could go back and forth with those. The bottom, the exponential and logarithmic formulas. The antiderivative of e to the u is e to the u. The antiderivative of a to the u, so this is probably one that you're not as familiar with, so that's good to have that sheet. The red box, the natural log of u, we're going to talk about that one in an example. And then the last one with log, so the antiderivative of log base a of u du. Sparingly, you'll see that. I might have only seen that maybe once or twice in working through problems. Okay, it's a good, nice to know that one, but don't get hung up on that one too much. Okay, all right, so let's take a look. So if I asked you to evaluate 1 over u du, and if I rewrote this using power rule to be u to the negative first, and I wanted to anti-differentiate u to the negative first, what would I do with that exponent negative 1? Add 1, so it becomes 0, and then I'm dividing by 0. That should throw off red flags in your mind. That cannot happen. Okay? So the antiderivative of 1 over u, we need to think, okay, what can I take the derivative of to get 1 over u? And that was natural log. Okay, this one is common. This is one you need to study, practice, be able to work with, because this one is very common where we end up with an integral with some function in the denominator that we are going to anti-differentiate, and we need to know that that ends up being natural log of u. They put u in absolute value because you cannot take a natural log of a negative number. And so it's absolute value, the natural log of the absolute value of u. Okay, so this one I just want to reiterate to you that you cannot use power rule on this. This is not power rule. Okay, so 1 over u, anti-differentiate becomes natural log, absolute value of u plus c. Now, if I were to flip this and say, okay, what is the antiderivative of natural log of u? Do not make the mistake and say this is 1 over u. Okay, that's very common. Do not make that mistake. Okay, the antiderivative of natural log of u is not 1 over u. We can look on our sheets, and it's actually this. U times natural log of u minus u plus c. So this is another one that you could see, and I've seen enough of these that these do occur. So do not make the mistake if you end up with an integral that's natural log of u and say, well, that's 1 over u. Not the same. The antiderivative of 1 over u is natural log of u, but it's not the other way around. All right, this one's kind of nasty. U, natural log of u minus u. Like, how am I going to remember that? Okay, let's actually show or prove that this is true. So that means if I take the derivative of this red box, u natural log of u minus u, if I take the derivative of that, I will end up back at natural log of u. Let's show that. Okay, if I were to differentiate, I would do each piece with respect to u. minus d du of u plus d du of c. All right, we want to prove that this ends up being strictly natural log of u. What is the derivative of c with respect to u? Zero, because c is a constant, remember? So this goes to zero. We don't have to worry about that. What is the derivative of u with respect to u? 1, but in this case we're subtracting it, so it'd be subtract 1. What is the derivative with respect to u of u times natural log of u? So this is product rule. Okay, so product rule, again, can do it as the first one stays times the derivative of natural log of u. What's the derivative of natural log of u? So 1 over u. It's with respect to u already, so we went u prime would be 1. So 1 over u plus the derivative of u, which is 1, times natural log of u. All of that minus 1. So really this is u over u plus natural log of u minus 1. U over u is 1. So positive 1 minus 1 ends up simply just being natural log of u. All right, so this is just showing that the original statement, well, shows this, that if we differentiate this, we end up with natural log of u. Today's section is difficult, or there's a twist to it, because we're doing derivatives and antiderivatives all within the same problem. And so we have to keep straight, okay, are we differentiating or are we anti-differentiating? We have to make sure we keep it straight what's going on. All right. If I gave you these two integrals, f of u du and f of u dx, and I say, are these the same thing? Okay, these are not the same. That differential is important. What is the differential in our integral? So the first one, what's our differential? du. And what is du? Changing what? Not changing u. So think of day one. How did we evaluate integrals using geometric shapes? It's the width of each rectangle. So remember, this would be the height, and this would be the width. So this is saying our width in terms of u and our width in terms of x. No, that's not going to be. So du is not the same as dx. So we cannot evaluate an integral until those are the same. And we'll do some work to make sure they are the same. Okay, so let's do a little practice here to show how things change based on if we have a du or dx, or an f of x or an f of u. So we have two functions. F of x is x cubed plus 1, and u is x squared. We want to find each of these antiderivatives in terms of x. So my final answer will have x and then some plus c on the end of it. So the first one says the integral of f of x, so it's the integral of x cubed plus 1 dx. What is the antiderivative of x cubed plus 1? Exactly. So this would be the antiderivative in terms of x. Now, what would f of u be? If I know f of x and I know u, what's f of u? So say it louder, Layla. Okay. So what are we going to have? And then what are we going to have after that? What's going to go after those parentheses? Well, so as initially du, so I cannot have an x and a u in my integral together. So I'm going to leave this in terms of u. So this is u cubed plus 1 du. Now I can integrate or anti-differentiate because I have both in terms of u. The one prior I had the x and the u, doesn't work. So this is 1/4 u to the 4th plus u plus c. But they do want it in terms of x, so now I'll put in my x value. So this is 1/4 x squared to the 4th plus x squared plus c. And so that becomes 1/4 x to the 8th plus x squared plus c. So we can't put in our x squared too soon. We have to differentiate when it's in the same variable first. Now part C, it says f of u dx. So now this one, because I know it's dx, I can make that jump and say x squared cubed plus 1. Because now I have them both in terms of x. And so that would be my integral of x to the 6th plus 1 dx. And so that ends up being 1/7 x to the 7th plus x plus c. So we do not get the green light to anti-differentiate until our variables are the same. Our variable and our integrand, remember this height of our rectangle is called the integrand, and the width is the differential. And so we have to have those in the same before we get the green light to actually anti-differentiate. Okay, so with all that being said, if my variables are different, I need to figure out a way to make them the same, and we can do that by substitution. And you'll start to hear me say U-Substitution. All right, means the same thing. You hear me say U-Substitution, we're trying to get it into a form where we can use some sort of substitution to make it work. All right, so a change in variables. So assigning an expression to u can often turn an unfamiliar integral into one that we can actually evaluate, because we're going to get more complicated integrands that we're trying to anti-differentiate. And so this U-substitution is a tool that we can use to make complex integrands a little bit easier to anti-differentiate. Okay, so it's not sufficient to change just f of x to d times d of x to some new function g of u d of x. Okay, so if we do this change, so this becomes a new function. So instead of saying f in terms of x, we have some new function we'll call g in terms of u. We have to address this differential as well. because what we saw in the last slide, those have to be the same variable. We can't do a g of u dx. It has to be the same. So a complete substitution, our new integral will be g of u du. Okay, and we do not get the green light to actually evaluate our integral until those match up. So we got some work to do to make those match up. Once we get them to match, then we have the green light and we can go ahead and integrate or anti-differentiate, same thing. Okay, so let's actually start doing some of these examples. So this is it in terms of the lead up to it. Now we got several examples that we're going to work through of actually doing the integration with U-substitution. Okay, so if I gave you this function, x squared times e raised to the x cubed dx. So our integrand here is actually a product of two functions, and it's not very easy to anti-differentiate in this form. So what I'm going to do, I'm going to start a u substitution, and I'm going to say, well, let's let u be x cubed. And we'll get into in a minute why I chose x cubed to be my u value. All right, I know if u is x cubed, then du dx will end up being 3x squared. Well, I could also write this. This is a differential that we did a few weeks ago, differential equations. I could also write this as du equals 3x squared dx. And I could also write this as 1/3 du equals x squared dx. Now, this treats as equivalent. Don't treat this as an equation you're trying to solve. We're saying 1/3 du is the same thing as x squared dx. And there's value in getting this to be just x squared dx, because this x squared dx, we already have up here an x squared, and we already have a dx. So I'm going to rewrite my integral. Instead of saying e raised to the x cubed, I'm going to say that's e to the u. And instead of saying x squared dx, I'm going to say that's 1/3 du. Constant multiple, because this is e to the u times 1/3 times du. So 1/3 I can bring out. And so this is now e to the u du as my integral. If I were to anti-differentiate e to the u, what do I end up with? Just e to the u again, but this 1/3 is still there. So it's 1/3 e to the u plus c, but that c just represents some constant number. So I can just write this as 1/3 e to the u plus c. I don't have to write it as 1/3 c. It's a number. Doesn't matter what the number is. And then last step, I'm going to put in what my u was. So this is 1/3 e to the x cubed plus c, and that is my antiderivative from what I initially started out with. Okay, so now the question should come up, well, why did we choose x cubed for our u? And we had x squared we could have chose. We could have chose e. We could have chose several different things. We could have chose it all at once. There's a bunch of options we could choose. Okay. We want to choose a u that when we find the derivative, it's already in the problem. Or we can easily make it in the problem. I'll explain that more in the next example. Sometimes it's trial and error to figure out what your u value will be. And that's the hardest part of these U-substitution problems. In your Math Excel assignment, the first few are going to tell you to use u as this. But then they're going to take that away, and you have to determine what you want u to be. Okay? We want to choose a u that when we find du dx, it's already in the problem. Or even more specifically, when we get to du equals something dx, that's already in the problem. And that's exactly what we did on this last page, is we got it to a point where we got x squared dx, and that was already up there in our integral. So we're essentially replacing x squared dx with 1/3 du. All right, so these are just some tips that I have for you, and this is not anything written in the textbook or anything. Just from doing these are the patterns that I've kind of come up with. If you have an expression in the exponent, so like that one we had e to the x cubed, or if you have 5 raised to the 2x plus 7, if there's some expression in an exponent, that's a good starting point. Try that as your u value. It may work, it may not. But more often than not, I've had success with starting with that to see if that will be my u value. Okay, so if you have some expression, not just a number, if it's x squared, don't put 2 as your u value, because then when you differentiate, you get 0. That doesn't help you out at all. Okay, so if there's an expression in the exponent, anything under a radical, so even if it's, and more often than not, it'll be an expression under the radical. If we had 3x plus 2 under a radical, say u is 3x plus 2, and then differentiate and see if that helps you out. Okay, so if there's something under a radical, try that. If it's part of a trig function, so for example, if you had tangent 3x, try 3x as your u and see if that helps you out. Okay, because tangent of 3x, that's a composition of functions. And so try 3x as your u value. If, say, you have a tangent function, tangent we can rewrite as sine over cosine. So sometimes writing it in terms of sine and cosine will change things up, and you can make it be the same thing that's already in your problem. Okay, so these are just some tips of where I start when I look at a problem. All right, I can't look at one and say, okay, yep, I know my u is going to be this. Sometimes you just have to try one, see if it helps you. You'll know pretty soon if it's working or not. And if it's not working, it's not taking you anywhere, stop, go back, try a different u value. Okay, let's try this one. So 6x times the square root 1 plus x squared dx. What should we try for a u value? Yeah, let's try all this. 1 plus x squared. Okay, and we could have taken x squared. We could have taken the whole thing 1 plus x squared. We could have taken 6x. There's different things that we can take from this. Let's try 1 plus x squared. So du dx, I know, is simply going to be 2x. So then du equals 2x dx. Well, this kind of helps me out because now I have an x being accounted for. I have dx being accounted for. But I have a 2 instead of a 6. There we go. Let's multiply everything by 3. When we do it on both sides, still maintains our equivalent expression. And so 3 du is 6x dx. So now I can rewrite my problem. And 6x dx is already being accounted for. All I have left is square root of u times 3 times du. The 3 will come out as a constant multiple, so I have square root of u du. That gives me the green light to integrate. What is the antiderivative of square root of u? Okay, so this is really u to the 1/2. So when I anti-differentiate, I add 1 to it, which is 3/2, and then it becomes 2/3 as the coefficient. So the antiderivative here is 2/3 u to the 3/2 plus c. So this is what I'm saying. On the right side of the screen, we are doing a derivative. On the left side of the screen, we're doing an antiderivative. So you have to make sure you're keeping straight what's going on, because you'll make little mistakes on, okay, what am I doing here? You'll differentiate when you should anti-differentiate. It's easy to do, easy to make those mistakes. All right, if I were to distribute the 3 in, I don't have to worry about the c, it's still a constant. So 3 times 3 here, so I have 2u to the 3/2 plus c. But then final answer, going to put back in what actually u is. So it's 2 times 1 plus x squared raised to the 3/2 plus c. Lena. Okay. So this is the antiderivative of this indefinite integral. Again, it's another function. It's not a number, because that c could be any number. And once we take the derivative of that, though, we end up back where we started. Okay. A few more examples. Sine of x times e raised to the cosine of x. Sam, what would you take your u to be? Good. Okay. So u will use cosine of x. Du dx, then what's the derivative of cosine? Negative sine of x. So du would be a negative sine of x dx. But our problem in red there doesn't have any negative. So let's divide both sides by -1. So it'd be negative du equals sine of x dx. So now we've accounted for this, and we've accounted for this. So now my integral becomes e to the u times a -1 times du. Bring that -1 out. E to the u du. My variables are the same, so I have a green light to integrate. Antiderivative of e to the u is e to the u. That negative comes along, plus c. Last step, putting in actually what u is, so cosine of x plus c. Not bad, right? Start to see the kind of the pattern, how these problems will play out. Okay. Let's do a couple more though. I'm going to keep increasing the difficulty a little bit. Okay, so this one, cotangent of 7x dx. So this is one that is, in terms of cotangent, kind of one of those tips. If we had tangent, I said write as sine over cosine. Well, cotangent would be cosine of 7x all over sine of 7x dx. What should we pick u to be? Okay, so if u is 7x, don't write this down. Watch. So then du dx equals 7. So du equals 7 dx. Does that help us at all? Okay, so this is what I'm saying. Sometimes you'll hit a roadblock, and you'll say, okay, yeah, I've accounted for my dx, but then I have a 7, so really I have cosine of u, sine of u. That doesn't really make things any easier. Okay, so that's why, all right, that didn't work. Scratch that, let's try again. So I'll give you the option numerator or denominator. So start to think. I'm going to pick one. When I take the derivative of it, I want it to already be there. So would I pick sine or cosine? Sine. Okay, and I'm going to do sine of 7x. So I'm going to take that whole denominator. What is the derivative of sine of 7x? Yeah, I didn't hear it all then. Kelsey, what did you say it was? Good. Okay, so the derivative of sine is cosine. Inside stays times the derivative of the inside, or just bringing it all out to the front. So 7 times cosine 7x. So du would be 7 cosine 7x times dx. Well, I have a cosine of 7x. I have dx. Let's get rid of this 7, bring it to the other side. So now I have 1/7 du equals cosine 7x. And that is helpful because let's rewrite this integral. So cosine of 7x over sine of 7x, I could also write as 1 over sine of 7x times cosine of 7x times dx. I could rewrite it that way. Okay, I could break up that fraction and say 1 over something plus this is essentially over 1, but I wouldn't write it over 1. I wouldn't need to write it over 1. Now, all this work we did over here on the right is helping us out. Because now, instead of saying 1 over 7x, I can say 1 over u. I can wipe out that whole bottom and say that's simply u. And the whole part after that, cosine of 7x dx, that's 1/7 du. So we have 1/7 integral 1 over u du. What is the antiderivative of 1 over u? So natural log of absolute value of u plus c. And so 1/7 natural log absolute value of u. U was sine of 7x plus c. A little tricky on that one, wasn't it? Okay, so that's why we're doing multiple examples, so you can see how these different ones can play out. So those tips that I gave to you, I mean, those were just that, tips. They're not in stone. It's not a guarantee that it'll work. Sometimes you have to play around with it to see what will work. Tangent, cotangent functions like this, the idea of being able to write it as a fraction and then split that up is a good way to look at it, because then we can get to a point, okay, yep, if I get it to a simple one, see, we were getting them all to like e to the u, 1 over u, square root of u. They're all very simple ones that we're going to work with. If you get one with u and there's still some junk attached with it, stop, go back, try a different u value, because it should come out to be something really nice. All right, keep going. This one will take a couple lines, so if you only got a couple lines in your notebook, flip it over. So they could write them this way. So our integral, and they're putting dx in the numerator, and then some function in the denominator, or actually this is a composition of functions. I often will simply just write this out for my own benefit. I say, okay, that's really 1 over cosine squared of 2x times dx. I don't know, my eye sees it better when it's written out that way than writing dx in the numerator. Okay. This one, we need to pick a u value. So this one, I will tell you, let's just go with 2x. So du dx is equal to 2. Du equals 2 dx. It doesn't help me out. So I'll go 1/2 du equals dx. So the only thing I've taken care of is the dx piece. So my integral becomes 1 over cosine squared of u times 1/2 du. We can bring that 1/2 up front. 1 over cosine squared of u du. Okay, 1 over cosine squared of u. Think trig functions, not any derivative rules. 1 over cosine is the same as what? Okay, so this is the same thing as secant squared of u du. All right, not any derivative rules. This is trig properties. Does anyone remember the antiderivative of secant squared of u, or what can I take the derivative of to get secant squared? Tangent of u. So this one's not so bad. The antiderivative of this ends up just being tangent of u. Now I want to do it in parentheses. So this progression here was probably the hardest part of this problem, is recognizing that 1 over cosine squared is the same as secant squared, and then recognizing the antiderivative of secant squared is actually one I can work with. So don't be intimidated by looking and seeing secant squared. That's actually one that I do know. That is tangent of u. And so this one, final answer, I would have 1/2 tangent of 2x plus c. Keep going. 2 more. Stay with me. No, I didn't. Oh, I misspoke then. There's 10 of them. And I'll tell you the 10th one is a homework problem. Oh. Sorry. Okay. Cosine cubed of x dx. All right, so I could also write this as cosine squared of x times cosine of x. So that means the same thing. All right, so starting to look ahead on this one, I'm trying to pick a trig function that when I do the derivative of it, it already appears. So right now, if I chose, say, cosine, I do the derivative, I end up with a negative sign. Sign's not in my problem. So I actually want opposite trig functions to appear in my problem. Cosine squared of x. Pythagorean identity. Do you remember what that's equivalent to? So think of Pythagorean, so right triangle. Nope. Okay, so if this was cosine and this is sine and this is 1, so cosine squared is the same as what? So this would be cosine squared of x plus sine squared of x equals 1. And so cosine squared of x is the same thing as 1 minus sine of x, sine squared of x. So this is the same thing as 1 minus sine squared of x. Now we have opposites. We have a sine and a cosine, or not really opposites, but I think of them in my head as they're opposites of each other. What do you think, or what would you want to pick for u? Okay, let's pick sine x. Because when we do this, we end up with cosine of x. So du is cosine of x dx. That's nice because that's all of this right here. So getting back to our problem, we have an integral of 1 minus, now instead of saying sine squared of x, this is simply u squared. Cosine of x dx becomes du. My integration properties, if I'm integrating and I have subtraction going on, means I'm going to integrate each piece individually. So the antiderivative of 1 would be u. minus the antiderivative of u squared would be u cubed and 1/3 plus c. Putting back in what my u is, sine of x minus 1/3 sine cubed of x plus c.